Hi. No pressure. Yeah, so I'm Yoav Weiss. I've been working on mobile web performance ever since mobile web was a thing, which is probably earlier than you think. I've been working on both the server side of things, trying to make content faster, as well as the browser side of things, making sure that we have browser-side features that enable us to accelerate content. And I'm here today to talk about something which is slightly depressing after all that time, which is why resource loading on the web is inherently slow, but also about how we can make it faster despite that fact. So just a short note, these are all, like, the illustrations are made by my kid, which is, like, she's way more talented than I am. In previous iterations where I did this talk, I would say here that if you don't like it, the illustrations, let me know. I'll tell her. She'll cry. It'll be good for her. But people were under the impression that she's 3. So she's actually 14. She's amazing. And this is how she draws when it's not her dad that tells her, draw this thing for me. But yeah, I've been in this industry for a long while now. And when I first started out, I was working on a web optimization proxy. And my first task on the job was to implement a client-server protocol, which is very much very similar to Speedy in order to be able to send multiple requests to the server at the same time and get multiple responses. And my second task on the job was to integrate an image compression server into that optimization proxy. And the image compression server component was getting very good results, was compressing the images by a factor of 2, more or less. And network bandwidth at the time, mobile network bandwidth, was a serious issue with the top-notch networks clocking at 33 kilobits per second, which is not a whole lot. But we soon noticed something odd. So even with these awful bandwidth, 2x improvement in image size didn't translate into twice as fast websites. Not unless we were deploying the image compression at the same time as we were deploying the Speedy-like client-server protocol. And at first, we were a bit surprised by that, because if we're cutting down the amount of bytes that we're sending down by a factor of 2, we should expect to see similar performance improvements. But what we soon realized is that on the web, the simplistic equations of time equals the bytes divided by bandwidth don't really apply. Downloading a website is not something we can consider just as if we're downloading a single resource. The contents of a website are discovered progressively, rendered progressively, and often continue to download beyond the point in which we consider the page as loaded. And one of the main reasons for that non-linearity was the impact of latency on the HTTP protocol. The fancy networks at the time were only delivering 33 kilobits per second, but they were also doing that with round-trip times of 700 milliseconds just for the radio layer latency, beyond considering the physical distance to get to the actual servers. So page load performance was primarily dominated by latency. But that was a long time ago, and the industry has moved on, and those problems are somewhat gone. So we have advanced a lot in the last 2 decades, almost. And things got significantly better, and we have improved image formats. We have better protocols. We have significantly faster computers, but we also have slower computers. and latency of the cellular networks have decreased significantly, but the speed of light hasn't changed much. It still takes a few hundred milliseconds to send light beams from one end of the world to the next. And content on the web has evolved significantly over that time period as well. From simple text websites, which occasionally download JavaScript to validate forms, we now have full-fledged applications. We have a full-fledged application development platform, and one where, at least by default, we download the entire app every time we want to use it, which is bonkers. And on that front, there's fundamental difference between the web and previous internet protocols, which simply open a connection, send a request to the server, and then get a response back. And the web also started that way, and HTTP 0.9 was a very simplistic protocol. But then, little by little, we added images and styles and scripts and fonts and videos and audio. And all these different resources now have to be downloaded together and in order to create the web page, in order to create the experience we want to deliver to our users. So today, I want to talk about how resources are loaded on the web and all the problems or all the hurdles that the browser has to go through, which make this process inherently slow. Then I want to talk a little bit about today's solutions for those problems and ways that we can already deploy and in order to avoid those hurdles. And I want to finish that round by talking about the next wave of innovation that's happening around those problems and how we're planning to solve that problem, solve resource loading on the web once and for all. So let's get started. Why is loading slow? What are the inherent hurdles that the browser hits when it's trying to load a web page? The first issue is connection establishment. When we start loading a page, once the user has clicked a link or wrote down a URL, we start the connection establishment process. And that's the first step that's inherently latency bound. And Natasha talked about that a bit yesterday. We have a DNS request with a reply in order to figure out the IP. Then a TCP connection is established. Basically, the client is telling the server that it wants to send the data, and the server replies back. Then TLS has its own version, which takes around 2 round-trip times, typically, because after the initial hello, the client and the server have to exchange keys. And that connection establishment process typically takes around 4 RTTs, which is quite a lot and makes that process latency bound. The second problem is server-side processing, where once we have the connection establishment parts, the client can send a request to the server, and then the server has to process that request and starts to send down a response. And that was the original, before Steve's seminal work on web performance back in 2008, kind of, yeah. Before that, that was considered the main problem of web performance. This is what people were optimizing for. And Steve showed that 80% of web performance is front-end bottlenecks rather than back-end bottlenecks. But that leaves 20% to be a back-end problem. And that's still, as far as I looked at it recently, and that's more or less true today. So we still have around 20% of the time that our applications are take to load held up by the server-side backend activities. In my previous job working for Akamai, we have seen numbers like 450 milliseconds for time to first byte in the median case. And I think that's not yeah, it's not atypical to see time to first byte that is even in the multiple seconds if caching fails and if various conditions are against the server there. So the next problem that once the server actually starts to send data down to the browser is slow start. When the server starts sending data, it basically needs to figure out how much bandwidth it has available to it, which is a process that takes time. And Natasha talked about that as well yesterday. But if you ever heard of the 14 kilobyte rule, where you have to put all the content that you want immediately rendered in the first 14 kilobytes of your HTML, slow start is the reason for that. Because the very first initial congestion window, the very first, the data is sent in the very first round trip time is today defined to be 10 packets, which add up to 14 kilobytes of content. So this is the amount that can be sent in the initial congestion, in the initial RTT, in order for the server to avoid congesting the network. Because congestion is a really bad thing that servers try to avoid. The fourth problem that once the HTML reaches the browser, the fourth problem now is resource discovery. When the browser starts receiving the HTML, it starts processing it, tokenizing it, which is breaking it down to different objects that spell out what the tags are, translating it from text to objects. And it does that in a streaming fashion and trying to figure out what are the resources that are needed for that page. It's done by the preloader, which is basically figuring out, like for example, here you have an SRC attribute. So this is what the browser will pick up and try to download. And that works well, but some resources are only discovered after creating the DOM tree or after style calculation happens in the browser or after scripts are executed. And yeah, we talked a bit about the critical rendering path, but basically the browser needs the HTML in order to create the DOM tree. It needs CSS in order to create the CSS object model that is attached to the DOM tree. And JavaScript, blocking JavaScript, can block both of these processes. And only after all blocking scripts are downloaded and executed, and all blocking styles are downloaded and applied, only then can the browser create the render tree, which leads to layout, which leads to paint, which is where the point in which the user actually knows that something is happening. So before the user sees anything, we have to download all those resources, which are not always immediately available to the browser. And there are also various priorities when downloading those resources that the browser applies in order to avoid blocking critical resources in favor of less critical ones. So the general rule of thumb is that HTML is more important than CSS, which is more important than JavaScript, which is more important than fonts, which are more important than images. But this is a very simplistic view of reality, and the actual internal logic is way more complex than that and takes into consideration the position of JavaScript in the page, whether it's async or deferred, whether images are in the viewport or not, and that is only for Chrome. And other browsers can have other heuristics, and the heuristics that Chrome uses can change over time. This is all unspecified territory, and this is all browser optimizations, which means that we cannot really we need to consider it, but it's complex to keep track of what browsers are doing on that front. And if we look at the resource download dependency tree, the browser starts out with just downloading the HTML, which then discovers CSS and JavaScript and images, often discovered by the preloader through tokenization. But then CSS and JavaScript can download more resources, which then can download even more resources, which means that we often find ourselves with deep and convoluted dependency trees, which for each layer in the tree, that's another RTT at the very least that the browser has to spend downloading those resources, and more processing time that the browser has to spend in order to process all those resources before it can figure out which resources they then download. So on the one hand, there's inherent tension here because we as developers love to keep our modules as modules. So it makes sense from a developer perspective to have our scripts load the other script that they depend on, or have our styles load other resources that they depend on. But from a user perspective, that makes our websites latency bound. So there is inherent tension here between developer experience and user experience. And as Adrian said yesterday, user experience should win on this front. But what these dependency trees cause is large bandwidth holes where the browser is downloading one resource in order, and then processing it in order to figure out what it has to download next. It means that there are times in which the browser is not downloading anything and the network is idle. These are wasted times. Okay, next issue, problem number 5, is queuing. And Natasha used the supermarket analogy yesterday, but I'm gonna, something that is more near and dear to my heart. I don't know how many of you travel a lot internationally, but there's always, when you're queuing up at the airport, there's always this one person at the top of the line that just now discovers that, oh, I have to take out my laptop, I have to get all liquids, and starts to take stuff out of their suitcase, and he's holding back more readily and more experienced passengers behind them. And that is, to me, a real-life representation of HTTP 1.1 and head-of-line blocking. So Natasha covered it yesterday, but yeah, essentially for HTTP 1.1, the downloading multiple resources takes multiple RTTs because each connection can only download a single resource at a single time. There's another source of unexpected queuing, which is buffer bloat. When a packet travels from your server to the browser, there are many queues that it has to go through along the way. And the server has its own sending queues, and network equipment can also introduce queuing. And queuing essentially is network equipment and servers trying to be helpful. They're basically saying, if I can't send this packet down right now because of bandwidth limitations or other constraints, I'm going to save it up for later and then send it once I'm ready in order to avoid losing that packet. That's naively helpful, but the result is that TCP's traditional congestion control algorithms, which are packet loss based, they see no packet losses, which means we can send more data. And then they just send more and more data until that buffer is full, which then results in packet loss. And only at that point they understand that, yeah, the bandwidth is limited and we should refrain ourselves from sending more data. But that means that that buffer bloat also creates a head-of-line blocking issue where resources that are already in the buffer will inherently be sent before resources that are coming in after them. And we'll talk a little bit more about that. The sixth problem is contention, where we have bandwidth contention. Often when we have multiple resources sent over separate TCP connections at the same time. And it's something we often see where the bandwidth is the bottleneck, which is good. But with HTTP 1.1, we have, like we said, 6 different connections downloading resources at the same time. So these connections, each one of them is handling congestion control on their own. Each one of them is figuring out losses on their own. And inherently, they will collide. They will compete over the bandwidth with one another and stall one another. And with HTTP 2, we were theoretically supposed to get rid of that problem. But since we have multiple servers and multiple H2 connections, we also often find ourselves with occasions where resources of low priority on one connection are stealing bandwidth from resources with higher priority on a separate connection. So bandwidth contention is still very much an issue nowadays. And finally, the 7th deadly sin of resource loading is bloat. The bigger your resources are, the longer it would take for them to download, the more time they will spend on the network and be vulnerable to bad things that happen on networks, like packet losses. And like Tim said, bandwidth and resource size still matter. They cost our users money. So we have connection establishment, server-side processing, slow start, discovery, queuing, bandwidth contention, and finally bloat. And let's go over those issues one by one. Starting out with queuing. So Natasha talked all about the problems with HTTP 1.1, or 1 in general, and how H2 solves all that by being able to send multiple requests and responses not at the same time, but on the same connection, and being able to perform header compression. And if we go back to the airport analogy, that's similar to the newer airport stations where you have multiple stations where people can prepare their stuff, and then the first one that's ready can go ahead and pass security. But H2 doesn't magically fix everything, it has a priority scheme, but we'll talk a bit more about why that's not particularly effective. Natasha talked about the packet loss, head-of-line blocking that H2 still suffers from. So since everything goes on a single TCP connection, if a packet is lost, that's delaying all the different resources behind it, rather than just 1 out of 6 that are in flight for H1. And this is a serious problem, but it's not the only problem with H2. Another problem is priority responsiveness. So H2 has different priorities that it sends to the server, and then the server can decide which resource it wants to send down. But because of the way that many H2 servers are implemented, and because of the way that there are effectively 2 different send queues for H2 servers, because HTTP2 is implemented in userland code, and then it sends all the packets to TCP in the kernel. TCP in the kernel has a separate sending buffer, and that means that it's very hard for the H2 server to control both queues to control what's in the TCP queue. So that often results in lower priority resources that were before the, that arrived to the server earlier, get ahead of higher priority resources in the server's queues. And the third problem with H2 is that we have no way to perform cross-resource compression. When H2 came out, we generally said that there is no longer a need to bundle resources together because requests now have no additional cost. So that is not 100% true. They have no additional cost on the network. They still have additional costs as far as the browser internal processing is concerned. But that theoretically could have been optimized away. What can't be theoretically optimized away is the fact that for H2, each one of the resources is compressed separately. Rather, like if you don't bundle them, each one can only compress separately, which means that in terms of data compression factors, we're getting significantly lower compression ratios when each one of the resources is compressed apart. So we could have benefited from cross-resource compression in H2, or that's the main reason or that bundling is still beneficial even with H2 on. So how are we planning to fix all those deficiencies? You could have guessed from Natasha's talk, Quick is the main answer to the head-of-line blocking issue. It's also because each one of the resources is sent over a different stream, and each packet loss is only delaying the streams that it has to delay because those streams were impacted by that packet that was lost. But Quick also fixes the priority issues because now the server only has a single sending queue. Unlike TCP, UDP doesn't have, UDP is a dumb protocol that's just, like Natasha said, throwing packets from one end to the next. So the server has to implement its own sending queue, and it can be a unified sending queue that is aware of resource priorities and can switch things around if a higher priority resource is available to send before a low priority resource is sent out. So Quick enables us to have smarter server implementations and smarter server implementations by default versus H2, which requires a lot of work to get things right and to shrink the buffers. Another very exciting development on the priority front is BBR, which is apparently bandwidth bottleneck. I don't remember, but I like to think of it as buffer bloat resilient. I saw that somewhere, and it's a better acronym in my view. But BBR, so traditional congestion control relies on packet losses as a loss signal. That is no longer needed in the world where, with Quick, we have explicit congestion notifications. So the server can know when congestion happened with Quick. Also, when we are looking at the RTTs, what happens when packets get buffered in the queue is that the RTT is growing until the buffer is full. So this is a graph that shows how much bandwidth is actually passing. And the green piece, the green part, is the part where buffering happens. So the sender is sending more bandwidth, but nothing else, no more bandwidth is actually being received on the client side. But the RTTs that the server perceives, the time it takes for the other side to acknowledge that data, continuously grows. So typical congestion control mechanisms operate on the right hand of that graph. So they're waiting for the buffer to be full and packets to be lost in order to start reacting. And BBR operates on the left side of that graph. So it's trying to recognize when RTT starts to go up and the bandwidth remains stagnant on the receiver side in order to figure out the ideal bandwidth that the sender should send down. So that helps generally for networks, but it also helps to significantly lower the amount of data that we have buffered around on our server, as well as in various network queues down the line. So BBR is a very exciting development on that front. And Pat Meenan, who's generally an awesome person, recently wrote about tackling that problem for Cloudflare, where he recently joined, by using BBR and setting some TCP parameters on the server. So his advice here is generally applicable to any all people that are running Nginx. He has fixed that for their CDN, but it's generally applicable everywhere that's running Nginx. And other servers also did a lot of work in order to optimize that problem. So this is definitely something to take into consideration. So the third problem is H2 compression dictionaries, where the third problem is cross-resource compression, and one of the ways we wanted to tackle that was H2 compression dictionaries, which is a way to basically create compression dictionaries from one resource in order to apply them to another resource. We have an IDF proposal, IDF draft on that front, but it's hitting a lot of security resistance, or at the very least, we haven't found a security person that will sign off on that and say, this will definitely not be a black hat keynote at some point, because there are a lot of problems that are related to encryption and compression. Compression often enables you to figure out encrypted content and get secrets out of encrypted content. There are many vulnerabilities around that. So we have a proposal, but it's not really getting a lot of traction. And an alternative approach to that very same issue, to the cross-resource compression, is a new standard called web packaging. It is a way to bundle multiple resources into a single package and then send them as a single resource, but keep them as separate resources as far as the browser is concerned. So the browser can process them separately and can also have granular caching for each one of them. So I have high hopes for this proposal to solve this, the cross-resource compression problem by replacing today's bundling of everything as a single big JavaScript block that the browser has to download in its entirety in order to process it with multiple resources that the browser can process in a streaming fashion. But still, keep the benefits of compressing that resource as a single resource. And yes, the server-side processing is the next hurdle because mostly for the HTML resources, they're often dynamic, which means that the server has to create them on the fly from data that it pulls from various databases in languages that are not always the fastest computer languages around. So if our backend times are slow, caching, when it's an option, should be applied, but it's not always an option. The early advice on server-side performance issues was to flush early. So not having to wait for your database to return its response before sending the head portion of the HTML to the browser, so to enable the browser to start processing it. The problem there is that you don't always know, and Andrew mentioned it yesterday, you don't always know the status of that HTML when you want to send it down. And that means that you'd have to change your page's logic in order to be able to switch that page around if it actually ends up being a 404 or a 500, and that's not always trivial. So one thing we can do on that front is to use a feature of HTTP2 protocol, which is called H2 server push, and enables us to send resources to the browser before the browser actually discovered and requested them. So in essence, it's using the wait time we see here in order to fill the bandwidth and start sending the critical resources earlier. And if we'll take a theoretical example here of HTML, like more or less 100Ks of HTML and then 100K of CSS and JavaScript, if we have to wait for the server to create that HTML, we have to wait many RTTs on top of that server time, where if we push that content, we can basically get slow start started on that TCP connection, push down all the critical resources in time for the HTML to be downloaded in a single RTT. But at the same time, H2 push is not necessarily easy to use. And yeah, for some reason, I can't seem to have any kind of, like, all my talks, there's Jake face on them. I guess it's, yeah, I guess now, yeah, joined Google, so I'm contractually obliged to just have Jake's face on each one of my talks, which works for me. But yeah, H2 push has many sharp edges, mainly around the fact that the server doesn't know what the browser cache already contains. So in many cases, for repeat views, if we're using H2 push, if we're doing it naively, we will re-push resources that are already in the browser's cache, which means that, you know, in best case, we spent bandwidth for nothing, and on the worst case, we're delaying the HTML or other critical resources which are not in the browser cache from being downloaded. So that's not great. One way we want to fix that is with cache digests, which is a new, an IETF draft that will enable browsers to send servers an image of everything they have in cache, and then the server can avoid sending those resources down because they're already there, so there's no need to. Another point where cache digest can be extremely helpful is with the web packaging proposal, because if we're packaging multiple resources with different caching granularities, very soon we'll find ourselves with multiple, like, with some of them being in the cache and some of them not being in the cache. And cache digest will enable us to then strip out the resources that don't need to be part of that package and send only the ones that are needed. So I'm super excited about that particular proposal. Moving on to discovery. Preload has been a recurring theme in this in the conference. So it's another, I don't know if recent, so a feature we added a couple of years ago, which enables you to tell the browser to kick off resource download ahead of time. Decouples, in essence, it decouples download from execution. So you can download the resource now and then execute it later, which essentially enables you to flatten out the dependency tree and make sure that the browser discovers everything ahead of time. So you don't have to download a thing to discover and download the other thing. You can tell the browser about that ahead of time without necessarily running it. Preload applies the default resource priorities. So we talked about the as attribute, as part of Preload. One of the things that it does is it tells the browser what is the priority of this thing that you're downloading. It's also required for various internal processing, as well as for the browser to apply the right CSP policy, the content security policy, to that resource. Another very exciting pattern here is that Preload, at least in the tag form, not the header form, but when sent down as a tag, enables you to have specific logic that tells the browser what to do once that resource has downloaded. So you can rely on Preload to get better script loading than what the default blocking or async or defer gives you. You can have custom logic for basically everything, not just for scripts, but use Preload as a primitive that enables you to build whatever loading pattern that you want, essentially. One thing that starts to worry me about Preload, though, that we see more and more people who are preloading all the things, and this is not a good pattern necessarily, because you want to preload only the resources that should be preloaded from the shape of your dependency tree. You also, because of server priorities, you want to be careful which resources your browser discovers before others. Because with HTTP2, browsers run a risk of sending your requests, even if they're low priority, they run a risk of being sent to the server before higher priority ones. And if the server gets those requests and it has the resources in cache, it can start sending those low priority resources before high priority ones, which means that they're now blocked in the queue, and buffer bloat is working against us, basically preventing the server from applying the right priorities. So you have to be careful, or you have to measure when preloading resources to make sure that they're not getting in the way of higher priority resources. This is something that I'm working on fixing, but it's a bit more complex to do that from the browser side of things. So generally, you need to be careful about what you're preloading and what you're not, and you need to measure whether that preload actually helps you or hurts you. And you can preload too much. And one exciting development for Preload is priority hints, which will enable you to not override, but tell the browser if this resource is a high priority or a low priority. Because today, when loading scripts, browsers guess whether they're high priority or low priority by their position or by the fact that they're async or deferred. But that's just heuristics which are not great. And it would be better for the developer to have an explicit way to tell the browser, this is important and this is not. So it should apply the right priorities, or even delay those requests from going out, or slow down, like throttle their processing versus, or favor high importance resources versus low importance resources. So this is another proposal that's in the works and going to be to go to origin trial very, very soon. So we've seen connection establishment as something that also takes a large number of RTTs, and it would be great to get rid of that problem or get around it. One way to get around it is using Preconnect in order to just get that connection establishment ahead of time and move it out of your critical path. So get all the handshakes out of the way. Another potential way to get rid of it is connection coalescing. So for HTTP2, if you have multiple hosts, but all of them translate to the same IP, and all of them are covered by a single certificate, then the browser will only send a DNS query to verify the IP of the different hosts, but then coalesce those connections together, so the rest of the connection establishment piece will not happen because it's not necessary. And in the future, as Natasha said, we have many protocol developments that will replace the handshake with a simple, hi, I'm sending you this, once the server and the client and the server are already familiar with each other, or replace it with a single RTT when they're not. The next problem is slow start and contention, and I put those two together because the answer is similar. We need to create a smaller number of connections between the client and the server. So unsharding your domains or make sure that they coalesce is one solution. One solution to that problem. Another problem that results in multiple connections is the fact that non-credentialed resources today are being sent on a separate connection. So typically fonts are being sent on a different connection, even if they are on a similar origin as other resources. So if you have third-party fonts, even if there is already an established connection to that server, another connection will be established in order to download those fonts because they're non-credentialed resources. I'm trying to convince privacy folks that this is not something that is actually needed for privacy reasons, or at the very least, it's not worth the performance pain, but that is a continuous struggle. And various developments on that front are secondary certs, secondary certificates, which essentially, even if you cannot have your servers reside on the same physical IP as one another or have them covered by the same certificate, you can essentially tell the browser, send it the certificate through the primary HTTP2 connection. So send it the certificate of that third-party host and tell it, I am authoritative for this host, so you can send those requests on the same H2 connection. And finally, bloat, and because I'm extremely behind here on times and PPK is mad at me, I will go over that quickly. So load only what you need is a very easy thing to say, is a very hard thing to do. But essentially, you shouldn't include entire CSS frameworks when you only need bits and pieces of it. You shouldn't include entire JavaScript frameworks if you can replace them by smaller ones. Code has costs with loading, with processing, so don't. Broadly is major compression innovation that can get you 30% lower bandwidth text resources. For everything static, you should apply it wherever possible. Responsive images and client hints will enable you to send smaller images down to browsers that don't need large images. And in the future, there are talks about a compression API that will enable us to do more client-side innovation when it comes to compression and have, for example, service workers that implement their own compression schemes that are based on gzip and broadly. So there are many plans on that front. So to wrap it up, we talked about the past, present, and future. What do you actually need to do today? One thing you can do is turn on HTTP2, turn on BBR on your servers. Those are things that are fairly easy wins. Use push, preload, and Preconnect. Use them responsibly, and don't overdo it because you can. Make sure you have a small number of connections to avoid bandwidth contention. So unshard your domains, coalesce your connections as much as you can. Load only what you need, apply broadly, And responsive images are awesome. I'm biased, but yeah. And other than that, know that future improvements are underway in order to fix this once and for all. Thank you.